a good idea. I think we should not write it. Yeah. Oh, you need to let that go. Okay. My uncle, wise man. And I have a hard time because he's like, it does really matter. So as much as you can, take it out. Being watched in your head. 5 bucks out of $10 books. Throw it away in the garbage. Hi. We need more answers. That's for the people who are taking AP this year. Yeah. Huh? Hello? Somebody left behind pages 33 through 40. So I don't know who it is, but somebody left them behind. 33, so you ended at page 32. You need to come back and get the rest of your pages. There we go. Okay. We are on page. Well, actually, I should let you get that into your book first. So once you have your stuff into your black duotang, you are going to turn in your black duotang not to the new stuff, but to the old stuff, page 59. Page 59. Still in the black duotang. Put that in your black duotang behind. Did you leave your sticky note on? Well, the sticky note was there to help you remember that that's where your new section starts. How are we doing? Are we ready? Yes, okay, good. Neutralization. We're going to do ionic reactions with neutralization. It's a good review because neutralization is just a special type of double replacement, and double replacement is on your quiz tomorrow, but neutralization is not, okay? But it'll be a good review because it's very, very similar, okay? So For each of the following, we are going to write the formula equation, the complete ionic equation, the net ionic equation, and we are going to identify any spectator ions. Now, there's a few things we are going to do. We are going to assume that all ionic compounds are soluble. So even if they're not, we're going to pretend that they are. So that means if you have a hydroxide that's not soluble, you're just going to be like, oh, well, I'm pretending it is soluble. Okay, so you're ignoring your solubility chart for this worksheet. Okay? Do you remember the difference between a strong acid and a weak acid? Yes. Yep. Yes, strong acids are completely dissociated, whereas weak acids, they are actually mostly undissociated. And this is important when it comes to writing an ionic equation. If you have a strong acid, HX, right? H was something, X, it will all be as H plus and X minus. If you have a weak acid, HA, is it mostly going to be HA together, or is it going to mostly be H plus and A minus separately? It's mostly going to be together. So when we write a weak acid in an ionic equation, we don't separate the ions, we write them together, okay? So we do not split them up. So weak acids stay together. Strong acids come apart. How do you remember which ones are the strong acids? So I brought no clean clothes. So I brought no clean clothes. It is right here. Or you can remember, who's going to help you out remembering that? Chloe Kleiberson will help you. Okay, so here's the Chloe Kleiberson. Or you can say, so I brought no clean clothes. They're right here. Those are your strong acids. Here's a weird one. If I give you H2SO4, you would think that H2SO4, that it would dissociate into two H's and an SO4 2 minus. Isn't that what you would think? Two H's and SO4 2 minus. But no, it dissociates. Only one of the hydrogens comes off. Okay, so just one of them is good. I know. And it's because H2SO4 is a strong acid. It comes apart completely. But HSO4 is not a strong acid. It is a weak acid, so it mostly stays together. Okay? So HSO4 is a strong acid. But HSO4 minus is a weak acid. So that second hydrogen does not come off to any great degree. The first hydrogen comes off completely, second hydrogen to no great degree. Basically, anytime you dissociate an acid, you should only be taking off one hydrogen. Okay? Remember, if you need to simplify the coefficients in the net ionic equation. And finally, if you have an organic acid, you're going to be taking off the final hydrogen, not one of the ones in the middle. Okay? All right, so let's try a couple of these together. Here we have KOH plus HNO3. And so we need to take our outside ions, which is going to give me K plus and NO3 minus. So I will get K NO3. And then I take my inside ions, and what do I get when I put OH and H together? Water. So you can write it as H2O, or you can write it as HOH, which might make your life easier for balancing later. Okay, so feel free to keep writing it as HOH, but in this case, the balancing is super easy because it is already balanced. What states should these be? Other way around. Yes, the water is liquid, of course, because water is at room temperature a liquid, and the KNO3 is aqueous. So now our complete ionic equation will do what we did with the double replacement. We will split up aqueous ionic compounds. It's aqueous ionic. So that's going to split apart into K plus and OH minus. HNO3 will split apart. Now, is HNO3 one of our strong acids? Yes, so I brought no clean clothes. Okay, that's NO3. So that's going to split apart H plus and NO3 minus. What have I forgotten so far? All my states, they're all aqueous. KNO3 is aqueous and ionic, so it should be apart. So we have K plus. We have NO3 minus. Those are both aqueous. And the only reason that there was actually a reaction here at all is that we have H2O, which is a liquid. That's our only new substance. Who are our spectator ions? Remember, spectator ions are ones that do not actually do anything. They just stay the same on both sides of the reaction. So who is staying the same? Potassium is staying the same, and nitrate is also staying the same. So those are our spectator ions. They are just watching the reaction, not actually taking part in it. So we have A plus, and we have NO3 minus. So our net ionic equation, I have, you can write OH plus H plus, OH minus plus H plus. I would find that weird to do because to me, the hydrogen always goes at the beginning. Like my cation, I like to have my cation first. So I'm going to swap it around, but it's okay if you don't. So H plus aqueous plus OH minus aqueous gives us H2O, liquid. Is good? Yes. You can just write HOH, totally fine. Yeah. Let's do the next one because it involves a weak acid. Okay, so you know what to do with a weak acid. So we have C6H5COOH, that is benzoic acid. Benzoic. Can you guess what the structure looks like for benzoic acid? We have a benzene ring with a carboxylic group, so we would have COOH. Yep, that's benzoic acid. Okay, so we have C6, 1, 2, 3, 4, 5, 6, H5, 1, 2, 3, 4, 5, and then a COOH. So C6H5COOH. All right, now we're going to remember it's this hydrogen that comes off. So we can't really do outside ions and inside ions for this one. We just have to say my cation goes with my anion and my cation goes with my anion. So this is my cation and that one's my anion. This is my cation, that's my anion. So the sodium's going to get together with the C6H5COO. So that's going to become Na C6H5COO, aqueous. And then, of course, H and OH are going to get together and form water, HOH, which is liquid. Now, for my complete ionic equation, is benzoic acid a strong acid or a weak acid? It is weak. Therefore, do I split it apart? Do not split. Okay, so it's going to be C6H5COOH. It stays together. Does NaOH split apart? Yes. So we have Na plus OH minus. How about sodium benzoate? Benzoate. Benzoate is the ion that comes from benzoic acid. Yeah, we've got sodium. It's aqueous, so it will split apart. So we have Na plus aqueous plus C6H5COO minus. And then, of course, we have water. Does water split apart? No, water is a liquid. It stays together. Do we have any spectator ions? We have sodium. Just sodium this time. So our overall net ionic reaction then would just be the C6H5COOH plus the OH minus. And then we would end up with C6H5COO minus plus H2O liquid. Okay, and yes, I'm going to be putting things on here like aluminum hydroxide. Just assume it's soluble because otherwise there's no interesting balancing to do. Try the rest. You know, do a few more there. That's not the one. That's not the one. Where are you? There you are. It's the blue one. There we go.
Thank you very much.
Yeah, no worries. There we go. Okay, cool. I just wanted to point out one thing that can be a little bit confusing, and that is, do you remember how I said that when we had H2SO4, when it dissociates in water, we get H plus and we get HSO4 minus. And that's important when you're writing the complete ionic equation. However, if you're writing a formula equation, H2SO4 plus NaOH, for example, You don't do anything different than you would normally do. You're going to put sodium together with sulfate, and you're going to put hydrogen together with hydroxide. Here's why it works that way. When you dump it into water, a strong acid dissociates, yes? That is a different process than when it reacts with a base. When you throw hydroxide at it, it rips off all the hydrogens. Hydroxide's like, give me hydrogens. So this is like the hydrogen is just floating away. This one's just floating away. But if I react it with hydroxide, it'll rip off both hydrogens. Okay, so when I actually react it, I don't end up with NaHSO4. I just end up with Na2SO4, and all of the hydrogens become part of water. Okay? So that can be a little confusing. Don't worry, we deal with it again next year. Okay, so if you're like, that made no sense to me, it's okay. We'll do it again next year. Okay? Hold on 1 second, sorry. Yeah. Okay. Hi. No neutralization on the quiz. Nope. Intra means within. Inter, as we all know, means between. So if we have intramolecular forces, we have forces within a single molecule or within a lattice structure. So intramolecular forces, those are all of our bonds. All the true bonds. I say true bonds because there's an intermolecular force that's called bonding but isn't really a bond. Love how they name things. So you got your covalent bonds, you got your ionic bonds, you got your metallic bonds. Those are your intramolecular forces, and they are strong or weak? Strong. They're also known as bonds. Now your intermolecular forces, yes? No? Okay. Your intermolecular forces are forces between different molecules, and we have talked about them before, but we have not given them specific names. There are 4 main types. There are other types as well. There are 2 other types as well. We may or may not get to those at all. I don't think they're really covered on AP, so I may just skip them all together. Okay? So we have dipole forces, which are between dipoles. So you need a polar molecule and a polar molecule. We have London dispersion forces, which occur between all particles, regardless of their polarity. I know, right? Well, then there's the van der Waals forces, but van der Waals forces could mean all intermolecular forces, or it could mean all intermolecular forces except for ion dipole forces, or it could mean dipole, dipole, and London dispersion forces, or it could mean just London dispersion forces, which is why I don't use the term, because nobody uses it the same way. I'm like, it's a stupid term. Your biology teachers may tell you about van der Waals forces. Go with whatever they say about it. I've yet to find a consistent answer on what actually are van der Waals forces. Like, no, as far as I can tell, some people use it one way, some people use it another way. I'm like, I just prefer to name all my intermolecular forces as they are, okay? Just go with whatever your current teacher tells you about them, right? AP does not use the term van der Waals force, not AP chemistry anyway. So dipole, dipole, and then we have the poorly named hydrogen bonding, which is not actually bonding, okay? Not actually bonding. Hydrogen not bonding. It's not actually bonding, it's an IMF, an intermolecular force. Now, just because I've used the word intramolecular, don't think that those are IMFs. When we say IMFs, we always mean intermolecular. And quite frankly, I don't know why we call them intramolecular forces when we just call them bonding. Do you know what I mean? Like they're bonding forces. And then finally, we have our ion dipole forces, which is between an ion and a polar molecule. So dipole, dipole, polar molecule, polar molecule. London dispersion forces happen between all molecules everywhere. And if you have problems remembering that, oh God, I just thought of this because I've been watching a lot of the Harry and Meghan, I haven't been watching them, I've been watching all the snarky commentary about them, okay? So there's been a lot of talk about the colonization and stuff like that too. So if you think about it, where did London go? They went everywhere. Apparently, there were only 17 countries in the entire world which Britain has not invaded. Only 17 in the entire world. I can't remember, but there's only 17, okay? Now, So where are London dispersion forces? They are everywhere. All particles, doesn't matter if they're polar, doesn't matter if they're non-polar. Intermolecular forces are, of course, weak. Hydrogen bonding is not bonding. So within the molecule, we have our strong intramolecular attraction, and then in between the two molecules, we have the weak intermolecular attraction. All, 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 all. Okay, all of the inter and intermolecular forces are based on Coulombic attraction, okay? Doesn't matter if it's intra or intermolecular, between the positive and negative charges. Let's take a look at this table and see what are the positive and negative things attracting each other. Tell me, in an ionic bond, what is the positive thing in an ionic bond? The cation, right? That's our positive thing. And our negative thing is the anion. What's the positive thing in a covalent bond? The nuclei are positive, and what is the negative thing? The shared electrons. In a metallic bond, what's the positive thing? Cations, and what is the negative thing? Delocalized electrons. Is this easy or what, right? Now, these are all of our bonding forces. And there's 1, 2, 3 of them. How many types of intermolecular forces are you responsible for? 4. Intermolecular. 1, 2, 3, 4. Ion dipole. Can you see how if you have a cation, it's attracted to the negative end of the dipole? What if we had a negative ion? It would be attracted to the positive end of the dipole. The one that's kind of complicated is hydrogen bonding. And so we spend an entire section just talking about that. But basically the deal is that you have to have hydrogen bonded to N, O, or F by a covalent bond. Yeah. And then we have to have an N, O, or F over here as well that has a lone pair on it. That sounds pretty complicated. Let's wait to talk about that until we've got focus on it, okay? So just be like, okay, it's still positive and negative, all right? Dipole, dipole, easy peasy. The negative end attracts the positive end. Dispersion forces, these are weird because what you have is you have normally a non-polar atom. It doesn't have any charge. Every once in a while, the electron clouds distorts. So there's more electrons on this side than on the other side, which gives this end a negative charge and this end a positive charge, but it's only temporary, okay? They're temporarily attracted to each other, so you get temporary dipoles, okay? So that's where we'll leave it for now. The exercises that go along with this, I'll leave that for after your quiz. Yes. And remember, on here it says, don't worry if you don't understand or can't remember the individual types of intermolecular forces. You're going to refer to that table anytime you want, okay? This is just to get you used to using the names, okay? Just study for your quiz tonight, no other homework. You're welcome. See you later. Jude, don't forget your phone.